Hello fellow radio amateurs, it's Joe here, ZL1PMY, and I've got in front of me now an Icom IC-7000, and it came in as not switching on. Now that's a fairly well known problem with quite a few Icom radios that have microprocessor control. Usually something goes wrong in the switching on cycle, but this radio was far more complicated than that. And rather than do a blow-by-blow repair, because it's taken quite a lot of hours to track down exactly what it was and a bit of disconnection of various things, I thought I would document it just in case there are fellow repairers out there who come across this. It's certainly not a fault that I've had before, and the component part that failed, I've not had a failure of that type of part before. So what we're going to do is I'm going to do a drawing, explain the logic of how it should switch on, and then I'll detail what the fault was actually tracked down to and the method we used to track it down. So stay tuned, as they say. So here we've got a diagram of the three major components of the radio set. You've got the PA unit, the main PCB, and the detachable head. And what I'm going to do is explain the flow of logic that makes it turn on, and then we can understand then better the fault that I'm going to describe to you and how that affected it not turning on. So up in the PA we've got a permanent 14 volts from our power supply, and that feeds a 3.3 volt regulator all the time, which feeds our microprocessor. We then have a relay, so when we press the on button, it's the relay here we can hear click, and that feeds power out to all the circuits of the radio set that need power. And one of those circuits is an 8 volt regulator which is fed by a 4R7 resistor, and that's IC-201. Our main processor is here, which is IC-302. And then we have the head connection, and the head connection actually changed pins. Not sure why they've done that, probably it was a mistake on a drawing board somewhere. And in the head unit we have another regulator which is fed by this 8 volts that produces 5 volts, and that 5 volts goes off to the logic in the head, and the 8 volts also feeds a boost converter unit. And the boost converter unit, it's like a mini switch mode power supply. It produces minus 15 volts and plus 12 volts. So what happens is we momentarily press the on button, and that pulls pin 135 down on the main processor, and 135 is pulled up by a resistor from the 3.3 volt supply. The microprocessor recognizes that you've pushed the on button, and it sends a signal out to a digital transistor that actually syncs the coil of the relay, thus turning the relay on, and then the power is returned to the rest of the set, which stays powered up until you press the button again. Now when we got this set, we found it wasn't turning on, it was clicking but not turning on. Now the clicking means that all this portion of it was working, but not turning on was something in this portion. And what we found originally was this 4.7 ohm resistor feeding this regulator had burned through, so that was replaced. And then we found the printed circuit track that went from here to the head had also burned through, and we had to take the board out, find that, patch it up, and because the track had burned, it meant that we knew there was a more serious problem somewhere. And so we started to look, and what was happening was the 8 volts here, if you put your voltmeter here, when you press the on switch, this 8 volts would disappear down to about maybe 4 volts if you were lucky, which meant that the boost converter was not getting sufficient juice to produce the plus 12 and minus 15 volts. So that started an investigation of where that current draw was going. It was obviously drawing heavy current. What we did in actual fact was take the head off and feed the head here with 8 volts from an external power supply and monitor the current. and we found the head unit was taking 3 amps when you pressed when you turned it on. In fact, you didn't have to press the button. And so a hunt started to see what could be taking 3 amps, and the fact that it was taking 3 amps and this voltage was sinking meant that the logic in the head never got going. And what we're going to do is look at the circuit of the head next, and I'll indicate what the fault finding procedure was, and then we can wrap the video up. So here you can see the schematic of the boost converter. The actual control chip is here. The 14 volts comes in through 2 inductors, and there are 2 switching elements, this FET here and this FET here. This one through this diode, which you can see is cathode to the output, is the minus 15 volts. That measured okay all of the time. This FET produces 12 volts, which goes out this way through its diode, which is here just on the sellotape. I hope you can see that. And this was the line that was failing. It was taking excessive current down that line, and that line feeds various parts of the head, including the display driver. Now what we did to fault find that, as I say, we powered the head up externally without it being connected to the set, and then removed first of all this choke and then that choke to see if where the power was actually going. And it turned out to be, let me look at it, L53, which is this one, which actually was taking the current somewhere, we didn't know where, and that's what the initial thinking was, that there was a short on the board. The only problem is, using our ohm meter, we couldn't find any resistance on that line greater than about 800 ohms. Should I say not lower than 800 ohms, which is fine. It should be able to provide current into that. And so that caused further investigation, and I'm now going to go back to the hardware and show you what's what. So here we've actually connected the 8 volts into just the 5 volt regulator, which will feed the microprocessor here, and we've isolated the buck converter. And now when we turn the power supply on, this is the 8 volt supply again, you see we've got 8 volts, very small amount of current, and on the actual chip, the regulator, that's the input, 8.2 volts, and that is the output, 4.99. so that is obviously working correctly. So what I'll do now is reconnect the buck converter and show you the difference in current consumption. So now I've connected the buck converter as well as the 5 volt regulator, and I'm going to switch on the external power supply. This is the meter to watch the current, and you see that's immediately 4 amps. The buck converter is producing 12 volts, but it's taking a lot of current while it's doing it, so we'll go through the circuit of that in a moment. So this is the back of the display unit. The blue wire here and the white wire are the 8 volts from my external power supply, which we use for testing. There's a gap just here, I don't know if you can see that, where that choke L53 has been taken out. I'm waiting for that to come as a spare. With L53 out, the buck converter ran, it produced 12 volts and it produced minus 15 volts. But as soon as you put a resistance from here to ground, i.e. a load, once that load got to be about 15 milliamps, then this converter started to take excessive amps. It went up to 4, depending on what load you put it on, and obviously that's not correct. You should be able to load this at least to maybe 75 or 100 milliamps without that happening. Also the FET, which is down here, started to get very hot very quickly, and so the tests had to be constantly interrupted while we let things cool down. At the end we changed the control chip, which is here, very small chip, and we also changed both rectifiers, and that made absolutely no difference. As soon as you put a load on that circuit, it started to draw a lot of current. So thinking of the burned out track, the burned out track, by the way, was caused by this electrolytic going short circuit, and that's on the 12 volt rail. So we had a short circuit on the 12 volt rail, which obviously punished the boost converter, and here's the 8 volt regulator, and you can see the track there just feeds into the converter, and that obviously placed a great load on the supply through the main board and burnt the track out. So having replaced the electrolytics, so there's now no short on it, we still had this problem of it sucking up lots of current at loads as little as 20 milliamps. And eventually we got to thinking that whilst it was burning out that printed circuit track, which would not be immediate, it might take maybe up to a second, it's quite likely that the winding in the coil has got really hot, and the varnish between the windings may have burned through and shorted out some of the turns, so the amount of inductance was less than the design. And we ended up buying this inductor. The original spurs are not available. I replaced that this morning, and I put a load on, the actual load, by bridging the thing there, the inductor, and this circuit now runs normally. So the cause of the whole scenario of not switching on was, first of all, this electrolytic going short circuit, which then pulled a lot of current through the 12 volts output of the boost converter, which caused that coil to fry and become shorted turns, and eventually the printed circuit on the main board back to the regulator that supplied it burned out, acting like a fuse. So that's it in a nutshell. I just thought that if anyone else comes across this fault, this little video may help in speeding that diagnosis up. I've never had an inductor go in a switch mode power supply before. This is the first time, and so I thought I would document it. Okay, thanks for watching, and we'll see you very soon. ZL1PNY is signing out.